time to get them answered. And basically, I'm just going to go through the syllabus in the picture, and I sent out an announcement about this, but a couple of folks, just in case you didn't see it, I posted a whole module about the final project, which also included a couple of papers from previous students, and I just wanted to mention a few things about those. Then, finally, I know that there's already a couple of folks that are interested in doing something around the SIR model in COVID. And so I just wanted to, so I sent out with the announcement, 538 has this great sort of a roundup of models. And a lot of them are based off of some flavor of the SIR model. So I wanted to also just quickly show you what I was talking about with that. So yeah, let's get started. So here we go. Chat up on one of these things at least. Okay, so the project itself is basically going to be consist of two things. It's going to consist of a paper. I would kind of like to shoot for around 4 or 5 pages. And the papers that I'm going to show you by and large did not do that, but I would say that you should always think of condensing your information down to its sort of barest, so that so that you're communicating the most information you can in the sort of most information rich but also clear way that you can. Usually longer papers actually tend to be less clear. And some of the most famous papers, especially in the statistics and machine learning world, may only be 4 or 5 pages long, but do significantly more than some of the 30 or 40 page papers I've read. So the project guidelines here. Okay, it's going to open up here. Great. So basically, what I want you to do is I want you to pick a novel situation or event or topic to model. So this can look like a couple of things. So this can look like you want to model, use an extension of the SIR model to look at a very specific situation. That's a great example. Or you want to take a population model that we've been talking about and apply it to a different situation, right? Like apply it to gentrification or something like that. That would be another interesting situation. You should always, at the end of the day, one of the requirements of this project is that if you're going to do a differential equations project, that you do write down some non-trivial extension of the differential equations that we've been talking about. So I don't want you to just take the SIR model and basically just repeat the analysis that we've done, or just take the competitor, the competing species model and just repeat the analysis we've done. You should write down new, but you should also just, for your own sanity, not make it too complicated. And as you troll around those epidemiological models, if you take a look at them, you'll find that a lot of them are actually relatively simple at their sort of in their guts. Their process of estimating parameters and their process of moving over a map, things like that, are potentially fairly complicated. But the model itself is very simple. And one of the reasons for that is that you'll find that if you start adding all sorts of crazy terms into your model, it becomes very, very hard to actually prove anything. We'll see that in the lab. So that's really what I want you to do. So I want you to come up with a novel situation, and it should be based on the real world, but it doesn't have to be an actual real world example. I'll allow you to sort of make some assumptions. And write down some novel equations that particularly reflect that example, but can of course be extensions of the standard equations. And then I want you to carefully think about and fit the parameters based on either some considerations or some data. And these are things where we'll talk a little bit about this next week, but in the case studies talk a lot more about how you select these parameters. We have been sort of talking about the models so far, but I will say something next week about how we actually select the parameters, especially in the case of the SIR model. Okay, so once you actually, so you pick your problem, you describe it clearly, then you write down your model, and you base your model on reasonable local assumptions that you describe clearly, right? Then I want you to actually do the kind of analytic work that we've been doing, right? The temptation, we have this very powerful tool, which is the, which are these differential equation solvers. But at the end of the day, I mean, one thing that we've sort of seen over and over and over again is that, we can fire a bunch of trajectories at, at a graph and try to determine the behavior. And that's great. But one thing that we really want to get out of these things is these kinds of like relationships between parameters, these exact relationships between parameters that really govern the behavior, right? Which tell us which parameters we want to wiggle around to have which kinds of results. And those are the kinds of things that we, get with the equilibrium analysis. And we'll look at a couple of examples of that today, especially when you have a large number of parameters. Sort of what do you do when you have, if you've got the SIR model, you want two parameters, right? And one of them is the length of the infection, and the other one is, some infectivity parameter that you can just fit by picking the top of the SIR curve. Well, it's not too hard, but when you have suddenly 10 parameters, it becomes a little bit more difficult. But so I want you to really do this analytic work, find your equilibria, classify them, draw the trajectory diagram, and extract some information from it, right? At the end of the day, in your problem description, the strongest sort of problems, the strongest case studies and projects that I've seen are ones where there's actually a question that is being asked and people are trying to answer. It's not just a sort of, well, let's think about fish populations in 3 pools and just say something about it. It's, well, no, there's a real question and we want to get a real answer out of it. So that'll be analytic work by 20. I also do want you to do some simulations, right? And these could be all kinds. So the simplest simulations, of course, would be something like looking at interesting families of solutions, right? So I should say, your simulations here should be like significant to the paper in some sense. I don't want you to just take your equations and, do some random simulations and put them in the paper and say, okay, well, here's what the solutions look like. They should either be important examples of families of solutions, right? So you say, okay, we've done our analytic work, we found out there's 4 families of solutions, and here they are. Boom, 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 boom. This is how the stability of the equilibrium, which is going to tell us how much chemical gets stored in between the blood-brain barrier. This is how it changes as we change the permeability of the blood-brain barrier. I want to see something like pretty exact like that, something that is, is really an asset to your paper, not just a, well, we're just going to take a look at some solutions. You should absolutely take a look at some solutions on your own time. But again, the kind of the point of a research paper, and you guys are grad students now, we're getting close to writing research papers, is to write something that enables the people that are reading it to not have to do the work that you've done, right? Like there are some people out at the extreme ends that are doing work that nobody else could do. But for the most part, academia moves forward because it's a sort of distributed labor pool, right? We do work so that other people don't have to, and then we read other people's work so that we don't have to do them. And the point of the paper is to do some work, get a nice analysis of something, and then explain it and present it in such a way that somebody else could follow your analysis if they wanted to, and can get everything that you got out of it, but doesn't have to do it themselves. So that's really in the writing where you're trying to go. And then finally, draw some conclusions. So basically, say, okay, so we did this analysis. What does this tell us about the situation that we were trying to model? Okay, so are there any questions about this? And I'm going to go through one or two of the papers and just sort of show you some examples of how this has gone down the past.
Hi, Professor. This is
Yeah.
Sai here.
Mm-hmm.
So, like, let's say we have some problems set in our mind and we have built a model for it. So, is it necessary for the parameters that are modeled by us to be so realistic? Like, we need to go outside and pick up some real world data and get the parameters so accurate, or is it okay if we do some simulation and put some meaningful values there? So what is the right way?
Yeah, that's a good question. So you can, so I would say you can kind of go either way depending, but just be careful about it. So it is completely fine to not go and take real world data as an example. For the sake of this class, I'm definitely going to allow you to do that. So in particular, I don't know if any of you have looked at the COVID, like the raw COVID data or something like that, but the Johns Hopkins data drop is just a nightmare. I mean, a huge part of what they're doing there is trying to compile the stuff because they've got they've got some hospitals that are reporting things every week. They've got counties that are reporting things every 3 weeks. They've got cities that are reporting things every day. They've got municipalities in Montana that are just reporting things completely randomly, and they're trying to then compile all of this data together into some sort of narrative. Into some sort of count of how many people are sick currently, without even doing any prediction or anything. It's a complete nightmare. And so, in data collection in general is difficult. It is something that so I will definitely allow you to not go out and collect data, but instead you should make some reasonable and substantive assumptions. And describe the reasonable substantive assumptions you're making and be clear that they are assumptions, right? You can, there's a lot in academic writing, which is just being clear about what you're doing, right? You're not cheating or pulling. That said, so this analytic work simulation modeling is a little bit flexible. So if you are interested, for instance, in really doing a deep dive into some SIR fitting from real data, right? If you say, okay, I want to use a susceptible, exposed, infected, recovered an SEIR model, and I want to really fit these parameters to data. So I'm going to go out and I'm going to collect, I'm going to collect 2 months of COVID data or something from one of these data sources. And then I'm going to go through the whole fitting procedure carefully. In that case, I'll definitely weight your analytic work a little bit differently than your simulation work, right? Because your analytic work there basically is going to be picking, carefully fitting the coefficients, whereas you'll be doing a lot more simulation work. So that is a little bit flexible, and we can certainly talk about. That's a little bit flexible, and we can certainly talk about that if you're interested in doing more of a data analysis, or even something much more theoretical. If you say, and I've had students in the past say, look, I don't actually want to do any of the simulation work at all, but I'm interested in actually proving something about a certain system of differential equations in a certain context. And that's when, oh, great, go do it. One of our students, I didn't include when working on some stochastic differential equations for some quantum computing stuff, and she just did her presentation on that. It's like, great, fine. So you're also free if you have other modeling situations that you want to pursue to just shoot me an email and we can talk about it.
Okay, so how about choosing some of the data sets from websites like Kaggle, etc.? So is that allowed to?
Yep. Yeah, so you can certainly choose like pull some data sets from Kaggle or something like that. I would say that I would like you to do either some differential equation simulation or something mathematical. I don't want you to do a completely sort of black box machine learning project here. So there can be, because there can be the temptation with like data from Kaggle or something to just say, okay, we're just open up scikit-learn and throw all these random classifiers at it. I do want you to do something a little bit more modeling.
Okay, got it.
But yeah, Kaggle is a great source for data sets, and I would say if any of you don't know about it, you'll hear a lot about it if you get anywhere adjacent to data science. It's a great source of data sets. It's a great source of learning, especially for like statistical programming. Say go there, if you find something you're interested in, take a look at some of the kernels. Be aware though, you should take anything anybody says about statistics on the internet with a grain of salt. There's a lot of bad statistical reasoning. Great statistical programming, right? So like Stack Exchange is another one where if you want to learn how to be a programmer, you will live on Stack Exchange, and it is brilliant for that. However, every single statistical answer on Stack Exchange is wrong. It's not. I'm just going to say it flatly like that. And the reason that it's wrong, especially for more advanced stuff, if you're looking at like, how do you fit a linear function or something, the reason it's wrong, especially for more advanced stuff, is because the most popular answer is the one that's considered correct. And usually people are more interested in a simple, less nuanced answer than the actual answer. So often what you'll find is that the most popular answer is actually incorrect for some sort of careful, finicky reasons. But yeah, so definitely take a look at Kaggle, especially if you want to make your models responsive to data. It is a great clearinghouse for data sets. And they also have competitions that go on. We had a Kaggle club last year that we were kind of getting going on a little bit, and then COVID shut everything down. So we may start it.
Probably once we take the machine learning course, we get a chance to participate.
Yeah, so I'll definitely see if I can start something up again this fall, because the machine learning course in the spring, and so having the Kaggle or substantive machine learning project. Any other questions? Okay, so I've got a quick guide to these papers. In particular, I have what they did right. I did not talk about what they did wrong. I think that it will become maybe clear when you read them. I want to say something about them. So, susceptible infected model for Lyme disease instance on Nantucket Island. So this is a great paper by Emily Trudell, who is actually a biostatistician at Children's Hospital in Boston. So this is, you should aim for this, but do know that she's been working in this industry for 15 years. But so what she did is she fixed a solid problem. She wanted to look at Lyme disease in the United States. She wanted to look at parasites feeding on deer, so a predator-prey-ish problem, but with the addition of an SIR model, so kind of mixing those two things together, interacting species and SIR. So she went through and did a bunch of careful kind of polling of data to try to get some reasonable estimates for her parameters. And then set up some initial conditions. And some of these are these are estimates. If you go through and read her paper, these are reasonable estimates. And something I would encourage you to do as well. She's very clear about what all of her model parameters are. And then she writes down, these look like complicated differential equations, but they're not the most complicated. They're not super complicated differential equations, in fact. The only really complicated thing are these Hill functions at the end. And basically, we'll talk about those a little bit, but these are things that start off flat and then interpolate up to something, and sort of interpolate between two behaviors. She did some simulations here. Her simulations, honestly, would be the one thing that I thought was a little bit weak in this paper. But she then went through and really solved this system of equations and pulled some substantive information out of it. She got a formula for a reproduction number, and then simulated some important scenarios of the disease-free scenario. So this is a really solid project to me. It is 11 pages long, which yours does not need to be, and concision is helpful. But she put a lot of work into this. And so again, if you look at this is like some sort of terrible pile of equations, but it's actually not that bad, right? You've got susceptible mice, infected mice, susceptible ticks, infected ticks, susceptible humans, infected humans. Great. So you just have 3 SI models, right? And you just have some medium of transfer between them. And that's really all that's going on here. It's just 3 SI models with some medium of transfer between the populations. Okay. Any questions? So this is another great little paper. So this is Chunli Chuang and Nehar Padar. And basically what they did is they took the SIR model and tried to extend it to rumor spreading and idea spreading. So this has actually been a really popular thing recently. And was to try to understand the spread of information and ideas on the internet. And this is a great sort of example of what you can do with paper. We take a known model and we apply it to a new situation, and we add in some new terms. We modify the model a little bit to understand that situation. So they go through, they write down some equations that are similar to the SIR model. And one of the nice things that they did here is they picked some initial parameters, and then they talked about how they developed this little table. So this is a great little visualization that they developed. So that's basically saying, so they have a whole pile of parameters in here, right? And what they're doing here is they're saying, so if we fix our parameters, the values that we want, and we change them by 10%, how does the does the equilibrium shift up or down? And this gives a great little guide to how you understand what it would mean to move your parameters around a little bit. These kinds of visualizations, basically anything that you can say about how your parameters or how your model responds to parameter movement is incredibly important. And then they actually did quite a few simulations here, and simulated in particular sort of interesting cases. And this is what you're seeing here is exactly that. Okay, so we figure out what the interesting cases are, and then we're going to show you, they figured it out by looking at the equilibrium, and then they're showing examples of these interesting cases. And then they also actually did a graph theory simulation as well that they spent quite a bit of time on, but that's above and beyond the scope of this. Any questions?
Hi, Professor. So when is our last week of class going to be over? I mean, when do we totally get to work on this final project?
So I would say you should start getting to work now.
Yeah.
Yeah. So I'm yeah. So full time. I'm going. So we're going to have an assignment this week. We've got an assignment next week, and then we're going to have a very light assignment. Where I actually may just not have an assignment the week afterwards. And they talk about differential equations, but give you that time to just work on this project. And then we'll see. This is the first time that I've run this class in this condensed format, so we'll kind of see where things are a little bit. My plan originally was to do the presentations during the last week of class, but we could easily push those off into finals week and just do the presentations during finals week. So, yeah, well, I may adjust that. I may adjust that deadline since I know it's coming up fast.
Okay.
Okay. Any other questions about, yeah, about anything? Okay, so the thing that I wanted to point out, so North American right whales versus fishermen with Edith. So the thing that I wanted to point out about this piece that Edith did, which I thought was important, was so Edith is from Maine, but then the other thing that she did, which is a pretty simple model. So she's looking at whaling and fishing, and in particular, whales getting caught in fishing lines. But what she uses this model for is to evaluate different scenarios. So she writes down a relatively simple model, and then she evaluates 3 possible scenarios as to whether or not, as to what it looks like for humans to affect whales, and what in particular that means for fishing quotas. And she does a careful job, and she really thinks about what the factors are, and ends, with some substantive conclusions, and with with an actual sort of opinion, backed up with some simulations. And she's very careful about her simulations and about, being clear what is, something that's proved and what's something that is, an assumption. But she uses her model to actually try to model different kinds of situations and then say something substantive about what the policy should be. So that is like a huge part of what you are trying, that is one huge part of what you're trying to do in mathematical modeling, right? So one goal is to just simulate, to project, to be able to do inference. Another goal is to be able to describe, right? You say, we found 4 causal factors and look, they perfectly fit the data. Like this seems to imply that we found an underlying mechanism. But another big one is to use them as a test case and to try to evaluate different strategies. And then finally, so Ru Bing in this paper, what she did here very nicely, so she wrote down some equations, basically for looking at infectivity in hospitals. So she proposed some equations, and then really what she did here is a very nice analysis in terms of the null clines and the equilibria of exactly what kinds of situations you could wind up in. And she actually had quite a bit to say about what the possible space of solutions was, even given some like relatively complicated equations. And the other kind of thing that she's doing here implicitly is she's comparing 2 very, very similar models and seeing where they come apart and become different. And that is another kind of project that you can do, looking at 2 different kinds of models for the same situation and seeing where they come apart, what their substantive differences in predictions are, and then trying to make some claim about what which model should actually be used, especially if you have some data in the background. And that can be data, whether it's a set of data points or some information about how the behavior actually is, right? You don't necessarily need a set of data points if you know that for instance the behavior is cyclic with a period of 3 years, right? That's a substantive piece of data that you can then evaluate your model on, right? If your model is predicting cyclic behavior with a period of, between 4 and 7 years, you can say, oh, well, that's pretty good, If your model is predicting, everyone dies out and that's it, well, that's probably not a very good model. Oh, sorry. Okay. Is the voice better now? Okay. Yeah, I did. Sorry about that. I did get a flash a second ago saying that my internet connection is unstable. So I'll try to not talk through that. Okay. So the last thing is I do want you guys to do a presentation. So the paper is going to be 80% of your grade. There will be a sort of 10 to 15 minute presentation. We'll just do them over Zoom. If possible for you, is currently not on the Jing. Okay, it's breaking. I lost it on one of my computers. Let me move really fast and see if I can get closer to the router. Okay, is it working better now? Just a moment. This has been my continuing adventures in trying to get the internet to work in various places. Okay. All right, so are there any questions about the final project?
Hi, Professor. This is Anjali.
Hi.
How much and what exactly is expected in the first draft?
So the first draft, yeah, good question. So the first draft is actually entirely for you guys, basically. So I would highly encourage you to do a first draft, but basically the first draft, I will look at whatever you have and give you feedback. That's what's expected. So,
Okay.
The closer you have, so that can be, and I will also do that for you basically at any point during the process. So if you write down a model and you want to send it off to me and say, hey, does this look good? I'm more than I'll look at it, I'll give you feedback. If you want to have a quick like Zoom chat with me, I'm more than happy to, or I can just give you written feedback and send it back. And then the first draft is basically, in some sense, that's kind of the deadline for me to look at your paper and say, this is what you could do to make this paper better. And that's why I have the deadline there, because in some sense, it's more of a, look, after this point, I can't look at potentially 13 papers. So. Any other questions? Okay, and do let me know if it becomes intermittent again. All right. Okay. So what we're going to talk about today is systems of equations with large numbers of parameters. Equations with, and we'll say large in quotes. And we may get to switching to the heat equations and spatial systems of differential equations. We'll see how far we get. The first part will be talking about systems of equations with large number of parameters. The second part will be going through the lab and homework. So, all right. The first model that we're going to look at today is the competition model. So this is another population model, and the idea basically is that, let's say that we have now two animals feeding off the same food source, two populations. X and Y. Feeding off same food source. So let's assume that they have logistic growth. So logistic growth when out of competition. And their competition is basically our standard competition of there's some probability that two animals will meet and come into competition, and some probability that if they do that, it will result in one of the animals dying. So the competition. Some probability I'll say population. Sorry. Okay, I seem to be back. I don't know what the heck is going on with the internet here. Okay. Can you all hear me again? Okay. Good. I'm really sorry. Thank you for putting up with this. I will. Sorry, I think we may have to suffer through this today and see if this internet stabilizes. And I will just make sure that this is not an issue for next class. So I apologize. So some probability the populations will compete, and this will result in one member of the population dying. And so then how do we write down our equations? Well, x prime is going to be equal to, there's going to be a birth rate and a death rate. So in this case, it's going to be well, let me just write the whole thing down. I think we're familiar enough at this point with these kinds of equations. So it's going to be some overall growth term minus a competition term with y, and then minus d is usually 1 over k for us, but we're just going to keep everything as a linear multiple for now, just because it makes the math easier. So this is the unrestrained growth, or the unrestricted growth. D is 1 over the carrying capacity. And C is the competition term. Okay, any questions? So, and if you have questions, this can include, I mean, so it could be that, you know, we've done enough of these population things at this point that all of these terms are completely obvious. So I would say secretly, right, we can rewrite this as a logistic equation, right? So if we wanted to, as beta 1 x minus x over k minus the competition term. So we could rewrite this in this form if we wanted to. But this is just kind of puts everything on the same footing. And of course, we're going to be looking for equilibrium solutions. So it's clear that this kind of gives us a nice way to have the equilibrium solutions factorized. But are there any questions? Do you believe that all of these terms here make sense at this point? Cool. Then I have prepared you for this point then. All right. So then y is going to be similar. This is competition. So these are basically going to be symmetric, right? They're not predating, they're just competing. So of course, C1 might not be equal to C2. It might be that when they come into competition, you know, 10 voles die, but only one, I don't know, rabbit does or something like that. So we're gonna have different rates here. So we've got this, and now we want to do our analysis. So first we want the null clines. And then we're going to want the equilibrium solutions. So we're going to have our x prime equals 0 null clines. That's not what I want. So we're going to have our x prime equals 0 null clines. And what are they going to be? Well, we're going to get 2. What are the formulas going to be for them? Oh, shouldn't it be C2 in C2x and y prime? Yes, you're absolutely correct. Thank you. I got these backwards, and I apologize for that. So what should the formula for the x1 or the x prime null cline be then, for the two formulas? Well, one of them is really straightforward, right? Everyone should shout out the straightforward one. Yes, that's actually, so we will definitely have, I might rewrite that. You're absolutely correct. That's what it's going to be. I'm gonna keep it though as C1y plus D1x equals beta 1. And then the other one is just going to be x equals 0. Although you're kind of right to write it in that way because we're going to want to write it in that way in just a second. With the third one being so I think we should get 4 between all of them. Unless I don't. So here we're going to get y equals 0, and then we're also going to get our d2y plus c2x equals beta 2. Yeah. Okay, so we get so we're going to get, sorry. So we're going to get our 4 null clines. And how many equilibrium solutions then do we get? Remember, the equilibrium solutions are intersections of the null clines coming from different from the different from setting the different equations to 0. So on Jolly's saying we get 2. What are the 2 that we get? Or which 2 are you looking at? 0, 0, absolutely. And you can just say, if you want, you can just say the other one. So I'm guessing that you're saying that the other one is the intersection of these two guys, right? Which is, I'll write the formula down, but it's not super trivial. So don't worry. Yeah. Yeah. So we also will get 2 more, because we also get y0 and this guy, and x0 and this guy. Yes, so that's exactly correct. That is this null Klein and this null Klein. I just rewrote the formula slightly by I just subtracted the C1y minus D1x. Sorry, I just added that to both sides, just to give it a kind of symmetric positive form. But you're absolutely correct. Yeah, those are the other two null Kleins. So we're going to have a beta 1 D1. So if we plug y0, so if we plug y0 into this, then we're going to get x equals beta 1 over d1. Great. If we plug x0 into this equation, then we're going to get, so x equals 0 into this equation, then we're going to get that y equals beta 2 over d2. And then finally, and I will write this down. This isn't super hard to figure out. It's just a tedious algebra. We're going to get C1 beta 2 minus D2 beta 1 over C1 C2 minus D1 D2 C2 beta 1 minus D1 beta 2 over C1 C2 minus D1 D2. So okay, so this is some complicated expression, but at the end of the day, I mean, it's just, you know, you can determine, you know, some solution to some equation over some determinant. And unfortunately, you know, so we would kind of like to stare at these things and say something about them, but we can already kind of see that this is going to be like, you know, non-trivial. So we can write down the Jacobian. Without too much trouble, right? So just looking at these equations and taking the derivatives, we're going to get j at xy equals, the Jacobian's not super complicated here, so the derivative with respect to x of this is going to be beta 1 minus, so I'm going to try to keep it in view, minus C1y minus 2d1. The derivative with respect to y is going to be minus C1x. Then the derivative with respect to x of this guy is going to be minus C2y, and the derivative with respect to y is going to be beta 2 minus C2x minus 2, oh, sorry, there should definitely be x there, minus 2dy. Okay, and we can actually then say quite a bit. For instance, if we want to talk about the stability of the points 0, 0, or even the stability of these points here, right? Just as a quick side. So the Jacobian at 0, 0 is going to be beta 1, 0, 0, beta 2. And so in particular, what type is that? Stable, unstable? Is the origin a node? Is it a focus? Well, given by our convention that beta is always greater than 0, of course, this is going to tell us that lambda equals beta 1, beta 2, all of which are greater than 0, and this is exactly unstable node. It turns out that you actually really can plug in these other solutions here and get something like reasonable. I mean, certainly you can see that for these two solutions, this is definitely workable. And you do actually get something like sort of reasonable for plugging in the other solution. Exercise. It's going to be defined beta 1, D1, 0, and 0, beta 2, D2. But this is definitely, you can see that we're in this kind of case where we are definitely starting to drown in parameters a little bit. And so it turns out this is another place where the trajectory diagram can actually be really useful. Let's draw trajectory diagram. And this is going to take a little bit of reasoning. Okay, so what do we have? So we have a trajectory diagram. We've got null clines at x equals 0, y equals 0, and then we've got two linear functions, right? Exactly as Anjali wrote down a second ago. We actually do want to think of these as linear functions, right? As x equals something, you know, something in terms of y, or y equals something in terms of x. But first, so our x equals 0 is going to be here. And our y equals 0 is going to be here. And we know that we have equilibrium solutions at beta 1 delta s or over d1 0. So let's call d1 0, and at 0 beta 2 over d2. And then we know something else, right? So we know that following lines so also we have, and let's write them in the way that Anjali had us write them. So we have y equals beta 1 minus, sorry, dx, d1x over coefficient here is c1. Great. c1, and then we have y equals beta 2 minus c2x over d2. And so in particular, since all the coefficients are positive, are these lines going to be increasing or decreasing? Exactly. That's, yeah, exactly. So the slope here is going to be negative. And so we sort of get a picture. And the picture is that, so somehow we have something that looks like this. So this is going to be kind of like a first attempt at a picture. Oops. Okay. And we see that, so this is first attempt. So we see that, as we expect, this is not an equilibrium solution, of course, because even though it's the intersection of two nullclines, they're two nullclines from the same equation. Neither is this. But we also see exactly where our final equilibrium solution will be, and it'll be right here. We'll just call this other equilibrium because I don't want to write that whole equation here. So of course, here's the thing. So I've drawn this picture, but it turns out this is not the only picture that we could draw. So let me draw you another picture that is completely consistent with all of the data that we have so far. So here's another picture. Okay. And here is our equilibrium. Oh, of course, we also have equilibrium. So here's our equilibrium, and here's our equilibrium. And I didn't quite draw this evocatively enough, but here is that we do have this other equilibrium solution. A little bit more evocatively. Okay, so that's a little messy, but try a little less messy. Sorry. There, that's what I want. This has been crappy art hour. Okay, so what we're seeing here is that we have a different situation. So this is completely consistent with all of the data that we had before, right? But the difference is that, well, we have our equilibria. We have 3 of our equilibria in the right place. And we have our lines going downwards, right? And the fact that besides positivity, we've put no restrictions on beta, D, or C. So that means that literally this could be any downward sloping. These could be any pair of downward sloping lines. The only condition we have is that it's downward sloping. So this is perfectly viable. And what this means is that, okay, so we have this equilibrium, but the equilibrium suddenly is not actually in the model domain. So this is a different case. A new case. Or I should actually say, because of course, what this secretly is this is a new phase, right? Completely consistent. With the above. Okay. So I'm going to draw these two phases that we've done so far. And I want to compare the trajectory diagrams for them. So in this case, we've got a simple one. We've got our equilibrium, our equilibria. We've got one at 0. We've got one here. We've got one here. We've got one where we cross. And we just need to do the trajectory plot. So quickly, we can either recall our equations, which might be good to do now. So our equations again are going to be x prime. So I want you to look at these two pictures here. Look at these two pictures and think about what the trajectory plots are going to be. Well, I just write the equations out quickly. Okay. So we can think about this asymptotically, but as a quick question, if I divide this up, so of course there's going to be 3 regions here. Let's start with this guy. So let's say that we have our regions 1, 2, 3, and 4. Region 3 is actually going to be the easiest, in my opinion. I guess region 4 is not that, so region 1 is not that hard to figure out. But what do we think? So what is the rough trajectory in region 3? And again, kind of the way to think about this, right, if you want to just do the quick asymptotic analysis, right, is to say, well, we should always, since the rough trajectory isn't going to change, right, because the rough trajectory, again, just being the sign of the derivative of x and the sign of the derivative of y, well, those can only change if we cross a null climb. So we may as well pick like an advantageous point, right? So if we're in region 3, we should pick a point very, very, very close to 0, right? Think about what happens when a point is very, very close to 0. Or in region 1, which is another good one, another kind of straightforward one to think about, we can say, well, what if we just pick a point where, x and y are very, very, very large, right? Close to infinity. What happens then? So for region 3 or region 1? For region 3. So in region 3, yes, okay. So if we think, here's how I would think about it. So we think in region 3 down here, it's either going to be minus minus or plus plus, right? So we're going to have something small, something small. Okay, well that doesn't really tell us anything. And then we're going to have a constant minus something small, and then a constant minus something small. So in particular, this should be in region 3. This should be positive. So in region 3, and I'll just kind of write that down. So here, beta 1 minus c1y minus d1 x is going to be less than 0. Sorry, it's going to be greater than 0. What am I saying? Since these guys are small. They are small. In this case, though, specifically, region 3 is the region where, this holds, right? Where beta 1 is greater than C1y minus D1x. So yeah, we're gonna get plus. Yeah, exactly. Okay. And so then what are we going to get as we go around the circle? So what about region 4? So again, quick way to figure this out. We only have first order zeros here. So in region 4, we're crossing the, oh Lord, which one? I think that's the x, yes. The x prime equals 0 null line, so the sign of x should change. And actually, the exact null line that we're crossing, right, is the null line beta 1 minus C1y minus D1x equals 0, right? So this condition exactly flips. So here, beta 1 minus C1y minus D1x is less than 0. This condition flips and we get the negative. Oh no. Okay. And then moving around, we get that this is going to be negative and this is going to be positive. And so without doing any work here, it's pretty hard to understand this central point as anything but what kind of equilibrium. A stable node, exactly. So the equilibrium is a stable node. And so this is great because basically, of course, we've talked about the fact that, like, you know, if we were showing some sort of like circular motion or something, well, we couldn't really say if it was stable or unstable. But in this case, I mean, we really can say it's stable. There's no real way that this could wind up being an unstable node, right? Or even a semi-stable node. We would have to have at least one arrow pointing away from the node. But here, I mean, this is making a fairly strong claim about the derivatives. We haven't said whether or not, you know, it's possible that you're spiraling in. We haven't said anything. So I should say, yeah, that it's stable. We actually, it's possible that it's a focus. In fact, it isn't. But in fact, from what I remember, it isn't. But either way, it's stable. Whatever is going on here, we are going in towards this thing. Okay. So any questions either about this picture, the stability, or the way that I got it? Okay. Well, in that case, let's do this one up here. So take a second and figure out the stability, or sorry, and figure out the trajectory diagram. And my hint here is going to be that we actually don't have to do any work. We know by exactly the same reasoning, we know what the trajectory inside that we know the trajectory close to 0 is. sort of wonder. I have the capacity to share a whiteboard, so I might do that in just a second. Okay, so what we're going to get here, just to show is, so again, when we're small, then the dominant behavior is moving away from the origin. And this sort of makes sense, right? Can we quickly discuss the signs? Yeah, in regions 2 and 4. So there's right. So there's two ways that we can understand these signs. So, or do you have a specific question about them? So the shorthand, I would say that the shorthand way to get them is to start with a known region and then just keep track as you cross the null lines, right? Because we know that confused in firmly determining the sign. Yeah, right. So if you want to do the heuristic way, which is you pick a known region and you cross the null lines, then that's kind of the simplest way. But okay, right. So let's think about what the conditions on region 2 really are. So on region 2, we need to be a little careful. So we just need to think about how we're defining it, right? So in region 2, we're going to have the equation. So 0 has some relation to, sorry, so we've got two inequalities defining this region, right? So the first inequality is in terms of the x null line. So it's going to be beta 1 minus c1y minus d1x is greater than 0. And so, and if you want to see this, we can figure it out a little bit. So in region 2, right, in particular, we're below, maybe I'll actually label these guys here. So just to remind us, this is the beta 1 minus c1y minus d1x equals 0 null line. And this is the beta 2 minus c2x minus d2y equals 0 null line, right? So if we have this region, so this region is somehow, so maybe has some relation to 0, right? So it's either greater than 0 or less than 0 question mark. And there's a couple of ways we can figure this out, but basically the simplest way is to say that, well, okay, so we have the line where we're equal to 0, right? And we want to fix that x is less than the x defined by that line, right? So basically, so we have two inequalities. So we've got this line equals 0, and we want points below this line. So the quick way for me to do it, the easiest way for me to do it is to just get all the signs positive. You can do it without doing that, but we rewrite this as b1 equals c1y plus d1x, right? And so if this is our equation, and we want x and y, pairs of x and y less than this, so we want, so we ask, what do x and y satisfy? sure, sorry, I should say what, let's just fix it. What does y satisfy? Fix x and y below this line. And it's going to be, so yeah, sorry, I should actually, clearly, so we should fix one of the variables. We're going to get minus d1 x equals c1y. So what happens if we make y smaller? Then we should have beta 1 minus d1 x is greater than c1y. So the region's defined by beta 1 minus d1 x minus c1y is greater than 0. By similar reasoning, we can look at the beta 2 equation. We're now going to be above that line. So if we fix, so we're going to have our beta 2 minus c2x is related somehow to d2y. Well, if we were on the line, they'd be equal. No, don't worry, because I was kind of brushing over this a little bit, and it is I don't know. Dealing with inequalities is always sort of like tricky. So of course we want this to be greater. It'll be greater. There we go. Check. And I also brushed over. I did want to say something about it because I also brushed over it on okay. Are there any questions? Okay, so a question for you guys then. So back to here, what we have, we've got this, then we cross the x null line. We change the sign of x, then we cross the y null line, we change the sign of y. And so what do we think is going to happen here? So just out of curiosity, so we have two cases. So in this case, it seems pretty clear that we actually reach a stable equilibrium, right? We've got two competing species, and eventually they wind up living harmoniously with some population in the middle. What happens in this case? So we have two competing species, and sort of what is generally going to be the eventual behavior? You know, up to heuristic trajectory sort of look at. Semi-stable in what sense? There's certainly semi-stable in what sense? So I'm kind of not saying anything about this equilibrium anymore since it's outside of the model domain. There's going to be some behavior that looks very semi-stable-ish, but can you just say another word about that? Let me just kind of draw on some trajectories, right? So it looks like what's going to happen is if we're here, we increase until we cross this line, and then we change sign. And we sort of just crash into we sort of just crash into the wall over here, right? There's like maybe other things that could happen, but we certainly aren't going to wind up crashing into the wall down here, right? And in this case, what does this mean? So what this means, what we're seeing here behavior-wise, is that X dies off. Exactly, yeah. X dies off and goes to 0. And so actually, because we have actually even have a slightly more dire situation. I mean, I can actually, I'll just say, you know, here I know more about the trajectory diagram we could draw in. But there's another set of information. This was the set that Sai asked about yesterday, if I remember right. Or sorry, on Monday, if I remember right. Okay, I'm doing it's not working. But was to say, well, what happens on the boundary, right? So when we're actually on the boundary, these equations are still well defined. One of them is just trivial, right? But we actually still have a dynamic differential equation in terms of the other one. And we see that on the boundary, of course, we're just going to get the logistic equation, right? So we're going to have increasing until 0 and decreasing until 0. And this is just going to be our standard logistic equation. And so actually we sort of know, let me see if I can, that not only are these guys going to have to crash into, not only are these guys going to have to crash into the wall, if they crash into the wall anywhere, they're going to go to the equilibrium solution, right? And since they never quite get there, then the actual behavior we should probably see is something like this. So what happens? X dies off and Y goes to the equilibrium solution. X dies off. Y goes to the equilibrium solution of Y prime when X is equal to 0. A to 2 over D2. Cool. So we fleshed out 2 cases. So I want to see if something works here. What other cases are there? So let me check something really fast. So we could, of course, do the same thing. So there's, I can draw a picture that is similar to this, but the other way, right? So what happens if we switch the color of these 2 lines? Right? This is a perfectly legitimate thing that we could do. What happens if we go like this? So in switching the color of these lines, right, what I'm doing is I'm switching which null line passes through first, right? So here again, this is going to be this. This is going to be this. We can decorate. So of course, secretly, I didn't draw them in, but for the X population, we're going to have the same thing going on. Oh, I'm sorry, there's not an equilibrium solution here. Okay, I guess we're going to live with that. got an equilibrium solution here. We've got an equilibrium solution here. Let's quickly draw on the trajectory diagram. The low trajectory is going to be the same. So now though, instead of crossing the X null line first, we're going to cross a Y null line first. And then we cross the X null line. And so we get the same behavior, but effectively reversed. So in this case, all the Y's die off and X approaches equilibrium. Okay, there's one more case. So there's actually, I mean, depending on how you look at it, there's 6 cases. But there's one more case that sort of doesn't fall into this. And we'll take a little break. But what we do, I want you guys to think about, so what is, so there's one more case where the behavior is substantively different. What is it? What is it? And once we get that, like, I do want to, specify that this is kind of a cool thing, right? Because we have like a lot of theory behind us, the theory of autonomous differential equations, the theory of semi-stable nodes. We know how to Taylor expand these nonlinear equations. But at the end of the day, we are classifying some fairly complex behavior just effectively by knowing, just effectively by drawing some pictures, right? And if we want to be very precise, of course, what we can do is what these pictures are doing is they're connecting. So essentially, which do I draw? I have 4 intersection points, 1, 2, 3, 4. Which line crosses which? And that actually exhausts all the pictures that we can draw. And then that exhausts all the possible behaviors. So I will leave, it is 2:35 my time. And so we'll be back at 2:45. And in the meantime, I want you guys to think about, so what is there's one more case where the behavior is like really substantively different. And what is it? And I'm going to go grab some coffee. So sorry, I'm still getting the copy made, but so parallel lines will so that will actually result in having the 3 equilibria. But the behavior will be the same as one of the 2 behaviors that we saw, depending on which order the lines are in, right? Because effectively, within the model domain, right? So globally, of course, this is completely false, right? Globally, we cross one of the lines and we get some kind of very different behavior. But effectively, in the model domain, the lines never meet. And so what that means is that even if we tweak them a little bit to be parallel, we would be drawing the same picture, roughly the same trajectory diagram. That's a good thought. Yeah, so that is definitely like one case that we could have. It's just, it turns out that that case is sort of qualitatively the same as one of the other cases we've looked at. Here would be the case where things look, the sort of the last case behavior-wise. The diagram that we draw looks almost identical to one of the diagrams we have here already. Okay, so formally be back. So any ideas? So what is the final behavior here? This, this. Any ideas? And if you want a whiteboard, I can give you a whiteboard and you can draw it. Actually, maybe I'll just do that really fast. Whiteboard. So you all should be able to draw on this. Let me see. Maybe you can't. Can you guys draw on the whiteboard here? Yeah, everyone should try. Okay, well that looks like a no. Okay. All right. So wait, quickly, can people still hear me? Just to make sure that we're all okay. So does anyone have any ideas about then what gives us substantively different behavior? What is the last picture? So it turns out that the answer is basically this first picture here, or the second picture, but with the lines reversed, right? So what happens if we have that and that? So this doesn't seem like the behavior should really be that different. So let me try to give ourselves. Let me try to give us some nice large. So it seems like the behavior shouldn't be that different. But if you think about it, so just quickly what's going to happen, so we're going to start in this section, moving outward. So we know that all the trajectories in this section are going to have positive derivatives in both, for both x and y. And then suddenly we cross the y null line. And so before, remember, we swapped x. Crossing the y null line, we'll swap y. Crossing the x null line, we swap x. And crossing the y null line again, we swap y. And so what we get here is that this is a semi-stable. Suddenly this equilibrium isn't stable. Semi-stable node. And in particular, what this means is that probably the population dies off, one of the populations dies off, but it's actually like really unclear which one. The population that dies off is going to depend heavily on the initial conditions. So one or the other population, I should say one of x and y dies off. but which one is going to depend on the initial conditions? Right, so if you remember, looking up here, these behaviors were kind of universal, right? Either everything falls into the equilibrium, everything, you know, X dies off sort of no matter what you do, Y dies off sort of no matter what you do. But in this case, suddenly we see that we have some really qualitatively new behavior, right? That depending, we have a situation here where one of the species is going to die off, but which one is going to depend on the initial conditions? So that is a very different phase, right? And that's the kind of thing where, so when you go out, if you were to think about this as like a biological model, or another place that this was actually used for, one of the other students' projects, which I pushed them, they did quite a bit with, but I pushed them to do maybe a little bit more with, was looking at competition in video game sales, actually. And so they were looking at concurrent players for video games and trying to apply a competition model to it, right? And what this is telling you is that depending on your parameters, which in this case are hopefully things you can measure, right? You know, what is the unrestricted growth rate? What is the carry capacity without competition? What is then the competition terms that you can go out and actually observe, right? That you can estimate whether you're in one of these cases where you're just inevitably going to get the population collapse, a case where you're inevitably going to get stability, or one of these cases where it really depends on the initial population. So are there any questions? Okay, so here's a quick classification. I'm not going to write the whole thing down, but this is how you should be thinking when you think about your paper and your own models, right? So we've done a good job of figuring out what possible behaviors are, but now we actually want to give a formula, right? We want to give some sort of substantive thing that you could go out and compute with, right? And so here's a quick classification. We're going to have some lines, and they are going to cross somewhere, right? So we have two lines. Just remind myself exactly what they are. Beta 1, yeah. So beta 1 minus C1y minus D1x equals 0, and beta 2 minus C1x minus, C2x minus D2y equals 0. What do we want to do? So the intercepts, we're going to call this lines 1 and 2. So the intercepts for line 1 are so the x equals 0 intercept is going to be when y equals beta 1 over C1, and the y equals 0 is going to be when x equals beta 1 over D1. So similarly, for equation 2, the x equals 0 intercept is going to be when y equals beta 2 over D2, and the y equals 0 is going to be when x equals beta 2 over C2. Right, our goal here is to write down some equations that you can evaluate. And so which of these intercepts maps to which point is going to determine exactly this behavior up here. Which intercept maps to which point determines behavior. So for example, if looking at the y-intercepts, right? So if we have that beta 1 over C1 is greater than beta 2 over C2, and so I'll drop a little picture over here. So what this practically means, right, is that the x-intercept is to the right of the y-intercept. And let's say that, let's look at the y-intercept. So beta 1 over D1 is less than beta 2 over C2. Then what that means is that the intercept over here, this is now less than this. And so we have an exact case. And that means in particular that we're in the semi-stable case. And so we could sit down, we could write the exhaustive list, but basically what this means is that by picking the direction here, so the behavior is in fact classified by the choice of these inequalities. Now, of course, this is more of an argument than a proof, right? And to make a rigorous proof, I would have to say something, along the lines of, essentially that what I'm doing here is I'm actually not classifying firm behaviors. What I've done is I've classified trajectory diagrams, but in this classification of trajectory diagrams, since these are atomic systems with differential equations, that blah, 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 blah. But for a general, if you're going to go and take like a PDEs class, that would be more the kind of argument that you need to make. In this class, though, and when you're thinking about your papers, it's more important to have some kind of heuristic like this, because this is and to give like a solid, firm argument for it, especially if if it's based on reasoning that could actually be proved if needed. At the end of the day, I would really like you to go and find these kinds of formulas that can then be used, right? Because until we sort of write this pair of formulas down, I suppose I should actually write this pair of formulas down correctly. Before we write this pair of formulas down, this is all well and good, and we've done some good intellectual thinking, and we can have some idea of what the system looks like. But it's hard to hand this information to somebody else in an actionable way. This gives them an actionable way. I tell them, well, if you tell me the unrestricted birth rates, and if you tell me the competition and the death, I can tell you exactly which one of these cases we're in. I've got a criteria for it. I've got formulas. I don't even need to tell you, you can tell yourself. That's really what we're looking for in the mathematical modeling world. We're building tools So we're building complicated models, but we're also giving tools to give to people that don't know the math as well. Okay, any questions? Okay, so let's look at another quick example. Modeling possums. So the idea here, and we'll go through this a little bit more quickly. I'm not going to do a bunch of algebra out, but do ask if you have questions. But the idea here is that we want to model possums with tuberculosis. Modeling possums with TB. And we're going to look at modeling possums with tuberculosis specifically for the application of trying to model solutions to try to evaluate population reduction strategies. Okay, so basically, so this is a case study that comes from New Zealand, where the possum population kept getting TB and then giving it to the cows, and then that, of course, was winding up with cattle wipeouts. And so there's there was some there's some impetus to try to figure out so what kinds of strategies could we use to deal with the problem, ranching standpoint. And so we're going to make the following assumptions. I'm going to kind of rush through these since this is SIR and we know it pretty well. So first, possum density is going to be given per hectare. So basically the number of possums per hectare. We're going to have two groups, susceptible and infected. S of T and I of T. And we're going to allow all these things to vary. So we're not going to assume constant population. And we're also not going to include a recovered population. So in this case, the disease is 100% fatal. So we have a background mortality rate. Background mortality rate is alpha years to the -1. Sorry, A years to the -1. And the mortality rate for TB, for tuberculosis, is alpha years inverse. And the contraction rate is beta. Which is in inverse possum years. Which is a great unit. so then what are the equations? So the equations are S prime equals, well, we've got possums being born. Oh yeah, B is the birth rate. So we've got possums being born from both populations. They're not susceptible. This is pretty standard from what we've seen. We've got possums dying of natural causes from background mortality rate. And then we've got susceptible possums getting sick. So then we've got susceptible possums becoming sick. We've got susceptible possums dying of TB and susceptible possums dying of natural causes. Great. So this is a very, very similar model to the SIR models we've been looking at already. No surprises really so far, but we'll see that like, even with the sort of small changes that we've made, we get some slightly different kinds of behavior. In fact, what this is most similar to is the model that we looked at the other day, where we just had a flat incoming population. Okay. So let's analyze. So our equilibria are straightforward. It's going to be at 0, 0. And then we're going to have one at alpha plus A over beta. And then I'm just going to state the result without forcing the algebra out. But it's going to be A minus B, so the overall birth death rate, alpha over A, divided by beta times B minus A minus alpha. So it's a little bit complicated, but it's not, I mean, it's not too hard. I had you guys go and figure it out. We've got the null clines. And this is going to be, well, basically, we're going to have, so the X null cline, I'll keep my conventions. X prime equals 0. The null cline, well, we just solved this for I. It's going to be I equals A minus B times S divided by B minus beta times S. And this is again where, so I mean, if you want me to pause and say how I'm getting these, please do, or I'm willing to say a few words about them. I probably won't do a whole derivation because this is just algebra. And this is algebra that we're pretty comfortable with at this point. But I will say a couple of words about some of these things. So this is one of our null clines, and the other one, of course, is going to be y prime equals 0, which is, well, we've got an I equals 0, and we've got an S equals alpha plus A over beta. Great. Okay, so we want to just, in understanding this a little bit, right? Let's take a moment to understand I equals A minus B times S over B minus beta S. So first, whenever you look at a rational function like this, what should you ask yourself? So if you think back to like high school, to like algebra 2 or whatever it's going to be, whenever you're given a rational function, what should you look for? If you need to draw this as an example. Rationalize. That I don't exactly know what that term means, but it may be absolutely correct. I may just know slightly different terms. Yeah, so we could certainly do that, but we kind of want to think of this as a function for the moment. Right, so we can get the, so denominator not being equal to 0, so what's another term? So, yeah, remember, so the denominator being equal to 0. And in particular, we can look for the asymptotic behavior, right? So the horizontal and vertical asymptotes. So we have vertical asymptote at s equals b over beta, and we have a horizontal asymptote at, in this case, it's just going to be the limit. So it could be a first order behavior in the numerator and first order behavior in the denominator. So when we take the limit, it's going to be I equals a minus b over beta. Okay. Otherwise, it's a rational function. Denominator, yes. Oh, yes, so you are correct. B minus a over beta. So now we can draw the diagram. And again, what this is doing is this is all giving us information about what the behavior is going to look like in terms of the parameters, right? This is a little bit hard to see how the parameters are going to work out. Although, of course, we can solve the Jacobian and and look at the stability. But we can get a sort of rough picture that's actually pretty evocative by working out this kind of behavior. Okay, so what do we have? We've got b over beta, s equals b over beta. We've got a, we've got I equals a minus b over beta. Thinking about this a little bit, this is, of course, this is going to come up like that. Actually, it's going to do that as well. Although I think that this winds up being under. I think that this. Oh, sorry, it goes through, yeah, sorry, it goes through 0. Great. Is there any rule that alpha is less than beta, or a is less than b? No, in general, there doesn't have, thank you for calling me on that, because no, in general, there doesn't have to be. In this case that we're modeling, there will be, because a being less than b, we can actually, so in general, no, and we actually see what's going to happen, right? So if a was less than b, we would be pulling this this line down to below 0 here, and that let's talk about it in a second, because so in this case, so in general, so in the cattle case, you're going to want to assume that a is actually greater than b. Otherwise, we would like to think the population die out, right? If the natural death rate, or if the natural growth rate is negative, and we have disease going on, then in theory everything should just, all the possums should die out, and there's nothing to worry about. And so we sort of in this case want to fix the a minus b to be greater than 0, but I don't want to necessarily do that, because the a minus b being less than 0 is actually a case that we should consider, and we will shortly. So yeah, it's a very, very good question. And I should probably have fixed it and then reeled it back, but yeah, because it will get substantively different behavior. And I would say as well, it's, I say if we have a negative growth rate and we add disease in, then clearly they die off, right? But that's not necessarily clear. We saw a case on Monday where, we were predating on where we had predators in the mix, and then we added in DDT that was just hurting the prey, and the prey in some cases seemed to thrive. So we have to be a little careful. Okay, so we've got this, and then where's our other, sorry, the null client is going to be when y equals 0, great, and then when, sorry, when I equals 0, and then when s equals alpha plus a over beta. And let me actually label my axes: susceptible, infected. Here is our equilibrium solution. Okay, so we can do our quick analysis. So for our trajectories, we can say, so what's going on? I'm gonna just, pick our favorite phase, pick the phase where things are very, very large. So when A and S are very, very large, I is going to be positive, and S is going to be negative. Great. So, decreasing in S, increasing in I. Then we cross a, sorry, this is where I'm, then we cross a I equals 0 null client, so I switches signs. We start decreasing. Then we cross a S equals 0 null client, and we switch signs. Again, this is also the case up here. This is all one nice contiguous region. Our null clients don't have to be, or null clients could be any analytic curve. Then we cross again, and go up here. Okay, so this certainly looks like we've got some kind of focus going on here. It's possible that it's a node. It's possible it's a node that we fall into. But what this is telling us is that we want to do is that we're going to need to determine the stability of this focus. Oh, sorry, the stability. And if it's focused or not. Okay, so I apologize. We of course also have an equilibrium point here. So I'll leave the equilibrium point at 0 for you guys to figure out. I mean, you can actually figure it out without too much trouble. But anyway, we can figure it out without too much trouble. But it's not kind of the interesting one. The interesting one is going to be this non-trivial equilibrium point. And so I'm just going to write down the Jacobian for it. So Jacobian at, I call this the non-trivial equilibrium. And what we get is that the Jacobian winds up being not great. B minus A minus A minus B alpha plus A over B minus A minus alpha, B minus A minus alpha, A minus B alpha plus A over B minus A minus alpha 0. Okay. So the reason that I want to write this down, though, is because this is clearly going to be hard to work with, and it's going to be hard to say anything about. So what do we do? Because we don't actually, you know, the temptation may be sort of throw your hands up and just be like, well, what in God's name can we do with that? And we don't want to do that. We want to actually still be able to say something. So, okay, so if what we care about is the stability, then what do we care about? How do we determine the stability? Exactly. We're just going to find the trace. And in this case, the trace is actually pretty straightforward. So the trace of J is just, well, algebraing this out a little bit, it's just these two things together. And so if you do a little bit of algebra, it turns out to be B times B minus A over B minus A minus alpha, which I could have written there, but this is more obviously what the, I'm skipping steps, and this is more obviously what you get in the Jacobian. Okay, so this is great because this, so trace greater than 0 question mark. And so in particular, this basically kind of answers itself, right? So if basically we know that B is going to be positive. So if B minus A is greater than 0, which generally is going to be the case that we care about, then the sign is entirely determined by alpha. So then it's stable if and only if, sorry, I shouldn't say that. Not if and only if alpha so if I want this to be less than 0, then alpha is going to have to be greater than B minus A. So great. So we can determine the stability, and we actually get, you know, as kind of nasty as that Jacobian is, we actually get a very straightforward formula. So similarly, it turns out, so node versus focus. Okay, so very nicely, actually, we can see that despite the fact that this Jacobian is looking ugly, the determinant is going to be really straightforward. It should be less than, no, because if it's stable, then we need the trace to be less than 0. And so if alpha is greater than B minus A, then the denominator is going to be less than 0. No, you're correct, because I was saying stable, 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 and then I wrote the unstable condition here. So yeah, that's a little bit more clear. So nodes versus focus. So for the node versus the focus, we just need to figure out what the determinant is. The determinant of J is actually really straightforward if you look at this, because it's just this, the top left corner is going to get multiplied by 0. So it's going to be A minus B alpha plus A. And so provided which is going to be greater than 0, provided B minus A is greater than 0. So one thing you can certainly say is that if the birth rate, so there's a couple of things you can read off of this, and in the interest of time, maybe I'm not going to say that much about it, but you can definitely say that the birth rate, if the birth rate is, sorry, I got this backwards. A minus B, B minus I. So if the birth rate is less than the death rate, then you're only going to have real solutions, is one thing that you can say. Just because then this will be less than 0, and so your 4 times the determinant, your minus 4 times the determinant will be positive, and so you can only have real solution. But okay, I do just want to, yeah. Yes, I think we have enough time to say something about this. So example further. So Roberts in his 1992 paper, and if you go in the book and you look at this possum example, it's an 8.3, then they cite the paper. Determined the coefficients to be the following. So determine the coefficients to be birth rate being about 0.305, background mortality to be about 1.05. This means that they live for about 9 years. Alpha to be 3. So alpha, of course, means that they're going to live with tuberculosis for 1/3 of a year, so about 4 months. And beta to be infection rate about 0.7. And I'll show you a picture of what this looks like in just a second. So importantly, though, what this means is that they found that delta is the square root of delta over 2, where delta here, this is our trace squared minus 4 times the determinant. So if we go and we plug these numbers in, we get a formula. And what we wind up getting is that this was I times 0.78. So what this exactly actually means is that yes, sorry, yeah, so you're correct, yeah, so it's a focus in the case that A is that the death rate is greater than the birth rate. But in this specific case, we find that the solution is oscillating. Here, it's cyclic. What that means is that it's predicting cyclic outbreaks. Cyclic population booms and outbreaks. And in fact, this imaginary part gives us the period, right? Because if you think about it, this imaginary part here, the solution is going to look like, recall what this is saying is that the solution is going to look like, S equals some junk, times sine of 0.78 t plus cosine of 0.78 t, roughly. And I is going to be roughly the same. So what this is telling us is that we can actually find, so this calculation gives us, we can find the period of the outbreak. Solution here is cyclic population booms and outbreaks, and we can find the period. just by omega is going to be 2 pi over root delta over 2, which is about 7.97. So what this is doing is this model actually predicts something substantive, right? You know, we're not just modeling for the sake of modeling. What this is, so even in the case that we have here, the model has predicted something interesting, that with no calling at all, just the natural cyclic cycles of die-off and population boom should be on the order of about 8 years. So sort of whatever patterns we're noticing, we should see them repeating themselves every 8 years. And that's actually a testable hypothesis, right? You can go out and check that. You know, that's something that you can give to the ecologists and do something with. Okay, any questions? So another example of what we can do with this is culling. So evaluating a culling strategy. So in this case, a culling strategy, we're just going to take a certain percent of possums whether they're sick or not. And let's call that percent that we're going to take off K. So we get new equations. So S prime is BS plus I minus A plus K times S. That's beta SI. And I prime is going to be beta SI minus alpha plus A plus K S. Oh, sorry, I. So the result of this calling strategy is just to take A and shift it by K. So what we've really done here is we've just identified one variable to shift around. We actually could have gone in reverse, right? We could have looked at this picture here for a while and said, well, okay, so what happens as we start moving things around here, right? So as we move A around, we see that what happens is this line moves. And we also see that that this line moves. This line moves. It's backwards. I totally did. Okay. Simon called me out on it already, and I still got it backwards the second time. All right. So what happens then is that this line also moves down, right? This asymptote. So as we increase A, we're going to get the null line moves down. This part doesn't move, but the null line moves down. And this null line moves over. Okay. Plus K. And of course, we can actually pull it far enough down. There's nothing to stop us here from actually crossing the 0 line, right? And it's entirely possible that we can actually pull this thing down so far that we cross the 0 line. And with a little bit of work, we can show that if we do that, then if we actually cross that 0 line, then we're going to change the stability, right? It's not even that much work. I mean, we can just look at this, right? So looking at the trace, if we shift the trace, we're going to have the trace of J is now going to be B times B minus A minus K over B minus A minus K minus alpha. And so actually, sorry, it's kind of important. We don't even actually have to pull it across the line before we can change the sign of this, right? We just need to pull it so that we just need B minus A minus K minus alpha to be less than 0. Now let's take a look at that. Ignoring the title because I didn't change it, and I apologize. Yeah. So here's what we get for the values that were as estimated by by Roberts. So for the values as estimated by Roberts, we get this nice cyclic behavior. And then we can ask ourselves, so then what happens as we change alpha, right? So as we add a little bit, add, 0.1. And we get some sort of weird cyclic behavior. Oh. So we add 0.1 and we still get cyclic behavior. What are we seeing here? So the infected population drops. Susceptible population eventually increases until the disease takes over again. And we're going to continue to see this sort of spiraling in. Although it's falling into actually, it seems to be actually falling into like almost stable closed orbits here. And so as we increase it, 1.2, still cyclic, 1.5, still cyclic, still cyclic-ish. But eventually when we get above about 0.2, the population just dies off, right? And so what we're seeing is that in 0.2, we can work out is exactly when we cross that threshold of changing the sign of the, the stability condition from positive to negative. And so again, so substantively what that means, so what is 0.2 in this case? Well, that's the percentage of possums that we have to remove from the system each year. And so what it's saying is that given the values that Roberts estimated, if we can cull 20% of the possums each year, then we can actually get to a place where we have where the population is under control. And in particular, where the infected population is under control. Okay, any questions? All right. So let's then take a look at lab. Okay. So what I want to do in this lab, this is can be relatively straightforward. There's really only one trick here. Is I want to talk to you guys about. I want to show you guys how to produce using NumPy slope plots and vector field plots. And this lab is going to be all going to use them quite heavily. So basically, slope plots and vector field plots they're pretty easy to produce once you have the code to do it. The only sort of trick is that you have to figure out how to supply PyPlot with an arrow for every point on the grid. Let's bring the chat window down someplace that I can see it. Okay, so we're going to have our usual imports. And then what we're going to use is what's called quiver. So the quiver plot function, basically, it's going to take a list of x coordinates and then a list of y coordinates. And then it's going to take a list of directions. So the x components and the y components of the vectors. So for example, if we want to plot like a vector like 1, 2 that starts at the point 2, 3, we would supply a quiver with 2, 3, the x coordinates, and then the direction that we want to point it in, 1, -1. There we go. Now we get a nice little arrow. So you can see it starts at the point 2, 3, and points in the direction 1, so positive in the x direction, -1. Okay, so one thing to note about Matplotlib is that it's always going to scale the arrows to be a reasonable size and only keep the direction. And you can change that if you want. So for instance, if you want to actually show the magnitude, then you can turn the scale off. But in general, like in this plot here, we don't actually see any magnitude. We're just seeing directionality. But especially for differential equations, the magnitudes tend to be so wildly different that it's good to just keep the scale on. Okay, great. So that's how we can plot one thing. Of course, we can move it around if we want, or we could add, we could add another arrow going a different direction. So now that we've given, if we specify the scale, then it will try to scale things up for us. So we add another arrow going a different direction. There we go. This is the scaled version where it's actually trying to point from 0 to a length of 1, 1. And so then the next thing that we want to do is actually look at plotting multiple vectors at once. And this is pretty straightforward, right? So just like our normal plotting with Matplotlib, we just need to supply all of the x coordinates in one call, all of the y coordinates in another call, all of the u components and all of the v components, right? So filling in here, if we've got two vectors, one starting at 2, 3 and one starting at 4, 1, one pointing in the direction 1, -1, they're pointing in the direction -1, 2. And to do it, we just collect all the x components, collect all the y components. So this is 3 and 1, great. So we've got our 2, 3, or 4, 1. U is going to then be 1, -1. And v is going to be -1, 2. When we plot the quiver, and there we go. There's our two arrows. All right. So what if we want to plot then something more complicated, right? Well, we basically just need to generate all the vectors. So for example, if we have some path, so for instance, path given by, x, some functions x and y, and we want to plot the derivatives, right? Then, so let's say we have as a simple example, just a path given by t to the minus 2t, and we can compute the derivatives. So if we have t equals np dot linspace 1 to 4 as an example, we don't want to include 0 here, of course, because we have negative exponents. Then the x component is going to be t to the minus 2. Remember that we have to use the double star for Python. T to the 2. This is going to generate for us our path, the x coordinates and the y coordinates, and there we go. Okay, except that I didn't spell linspace correctly. T.plot. Okay, great. So this is our path. So now all we need to do if we want to produce a quiver, right, is just, in addition to this, compute the derivatives, right? So u and v, well, okay, what's the derivative with respect to t of t to the minus 2? Well, it's going to be our minus 2 times t to the minus 3, and 3 times, sorry, 2 times t. Oh, that's very incorrect. Then we can add the quiver plot. And okay, there are our little arrows there. And of course, we can see that things are getting crowded, so we may want to do something like redefine t slightly to have, say, only like 10 points. Oh, sorry, which now it's, sorry, can't do that because now it's repeating that completely. I need to redefine, get a slightly less smooth line, and there we go. So we've got 10 of our x positions and our y positions. Oh, that's strange, something's gone wrong there. Oh yeah, okay, so this is exactly what this node is here. So if we look at this, so something has gone kind of wrong here though, right? Because the arrows aren't actually pointing in the direction that we want them to. And so the reason, and this is either stupid or not, depending on how you look at it, is that Quiver will always actually interpret u and v as not being scaled coordinates, but as being unscaled sort of coordinates as we see them as the viewer. So in this case, so it will always interpret something, pointing at what we would say is 45 degrees. So a vector pointing in the direction 1, 1 as 45 degrees on the screen, no matter how the axes are scaled. And so what we have to do is we have to go through and tell it to use the angles as specified by the axes. So in this case, we do that, and then all of a sudden everything aligns up exactly as it should. Okay. Any questions? Okay, so this is like, we're very close now. We're nearly done. We know how, so these are derivatives. We can now produce a bunch of arrows that are pointing in the directions of the derivatives that are actually going to correctly follow any solution curves that we draw. So the final question is, how do we just now go through and do this for an entire grid? And there's a simple answer, which is kind of the incorrect answer, which would be to use a for loop. In fact, we don't want to use a for loop because for loops are kind of computationally expensive. We have to do things many, many times. We have to make many, many, many calls to the function, to the plotting function. Instead, what we would like to do is produce a big matrix. So a matrix of all of our x coordinates and then a matrix of all of our y coordinates. I have about this down here. Yeah, so we want to produce a matrix of all of our x coordinates, for instance, a matrix of all of our y coordinates. And then we want to produce a matrix U of all of our x components and a matrix V of all of our y components. And so for instance, let's say that we wanted to plot vectors at 1, 2, 3, and 4, 5, 6. What we need then for x and y is a grid of 9 points, right? Just like we're seeing here. So x is equal to 1, y is equal to 6, x is equal to 2, y is equal to 6, blah, blah, blah. So then our x matrix, our x coordinates will be put in a 3x3 matrix of just the x coordinates, right? So 1, 2, 3, 1, 2, 3, 1, 2, 3. And our y coordinates will be put in a 3x3 matrix of just the y coordinates. So 6, 6, 6, 5, 5, 5, 4, 4, 4. Again, we're counting up from y being at 0 in this case. Okay, so we need to figure out how to build such a matrix, right? So if you give me a range in x and a range in y, how do I build these matrices again without using a big for loop? And the simple answer is that we use what's called a mesh grid. I'll show you how this works. So if we do np.meshGrid, and we need to give it our x and y. So we give it 1, 2, 3, and we give it y equals 4, 5, 6. Then what it returns is exactly our two grids. So if those of you who are coming from MATLAB, this is the same mesh grid that is often used in MATLAB. We could of course specify something slightly different, and then again, it'll produce the coordinates, the two-dimensional coordinates in this case. And so then we just save these out as x and y. So here's our x, and here's our y. And in particular, yeah, so that's a good question. So of course, what I put up here is 6, 6, 6, 5, 5, 5, 4, 4, 4, and what mesh grid is returning is 4, 4, 4, 5, 5, 5, 6 by 6, 6, 6. It doesn't matter in this case since we're just going to read these as coordinates. So when we feed them in, it's going to basically loop. Quiver is going to basically loop through these and find all the pairs. So if you think about it, so if we do, y1, 2, sorry, if we were to do x1, 2, y1, 2 is a tuple, we could loop through all these and produce all the tuples like this. And that's not going to matter if it's 4, 4, 4, 5, 5, 5, 6, 6, 6. Certainly if the order matters, so if you were trying to display this as an image using something like ImShow, then it would. You'd get an upside down image. But Quiver is just going to interpret this as a weirdly shaped list of coordinates. Yeah, that's a good question. That's an important point. Screen problems for some reason. Okay. So as an example, we can mesh grid our things together and then produce a big list of, a matrix of what we want our values to be and put them together. We can also, though, and this is one of the great things about mesh grid, is that we can, we can also use x and y then in our formulas. So for instance, if I wanted to say, well, u equals x times y, and v equals x plus y, we can use this to do all of our computations, and the computations will be done, each of these operations here will be done component-wise. So even though this looks like a matrix, it will not be interpreted as a matrix by NumPy, since it's not a matrix type object. So all of these will be done component-wise. Okay. How do we actually then do the 2D vector field from a differential equation? So if we have a 2D vector field, get some system of equations. So we can define a model just as before. And basically, we're just going to use this model now for exactly what ODE was using it for before. It was just to get the derivatives, right? So I can define, this model. So this is just going to return these formulas here, and I can say, okay, so now I want the derivative at, the point 1, 2. Oh, sorry. To give it, I want the derivative at the point 1, 2 for time 0, and it'll give it to me right there. Great. So what we can do now is this will actually, because Python plays very, very, very nicely, and in particular NumPy plays very, very, very nicely with the underlying Python operations, we actually can pass this guy, a vector of matrices, and it will just go through and do all the computations exactly as it did them up here without complaining. It will just do them component-wise and return a matrix of the results. So let's generate our x and y values. So let's say that we want x to be between space, I don't know, 0 and 4, and y to be in between 0 and 4 as well. Wow, okay. So then I'll use capital X and capital Y for our mesh grid. It's going to yell at me, isn't it? Yes, it is. Because I misspelled things. Great. And then I can feed, so I can say, well, I want U and V, right? This is going to return 2 components. I want U and V to be the derivatives at each one of these points, X and Y. And too many values to unpack. It's going to, right, sorry. Need to put these in a list at time 0, and there we go. So what it's done, because again, since this is all being done component-wise, so Python doesn't really think of these as being more than just component vectors. It's just going to go through and do these component as basically lists of elements component-wise, and then return, what's a shaped list of U and V values. So we can plot the quiver, and there we go. Oh, again, we should always do, sorry, we actually want to make sure that this is responsive to the true world directions. So we should always include that. Brilliant. Any questions? Okay, we can also put a solution in there, np.linspace, t equals np.linspace. Let's say 0 to 5 for now. Solution is ODE int. Let's start at 1, 1. So a good starting spot, 1, 1. T is equal to T. Oops. Model 1, 1. So model. I have to get the order here correct, otherwise things will get crazy. Great. And then let's plot solution. Oh, and I always get this backwards. Solution. Yep, got that backwards. And there we go. So here is our solution following this curve. Well, no, that shouldn't be quite correct. Okay, anyway, I apologize. Sorry, I apologize. In the interest of time, let's move on. Okay, yeah, I guess that is what we get. All right. Okay, sorry, there's something funky with the code there. But... Okay, so you can use this, yeah, so you can use this to produce these fairly nice, so you can use this to produce fairly nice plots with solutions. And just in the last minute, so I kind of want to say, so what I want you to do here, so what I want you to do here, what the homework is going to consist of is two parts. So the first part is going to be looking at the predator-prey equations where the prey population has a carrying capacity. And this is going to be mostly analytic, but I want to encourage you guys to simulate things, to take a look at them. Basically, what I want you to do is the kind of analysis we've been doing over the past few days. So write down the null lines, the equilibrium solutions. There's two rough cases depending on the parameters. Basically, all of these equilibrium solutions lie in the model domain, or one of them doesn't. So show me what those two cases are. Compute the Jacobian matrix. You do not have to compute, so I just want to see the Jacobian matrix. You don't have to compute it at the equilibrium points. And then the final thing is I'd like you to argue, either using the matrix or the trajectory diagrams or a combination of both, what the equilibrium types for the solutions are in each case. So just, you can either compute it and just find the stability explicitly, or you can argue using the trajectory diagrams. And then second, we're going to look at this geese-defy mathematical conventions case study. So here's the link, the journal link, and you can log in with your Northeastern ID and get access to the journal. But basically, what they were looking at is they're looking at a certain sort of paradoxical situation where you have herbivores with no predatory pressure on them at all, that still abandon feeding sites when food gets too abundant. They've got kind of a couple of things that they think may be going on there. But they wind up writing down these very complicated nonlinear equations, right? So these are equations that we really have no hope of solving. We don't really even have any hope of solving these things like for clear expressions of the equilibrium solutions, right? Like this is just going to be, we can see that we're going to have some null line here, but this is just going to be some sort of madness, right? How do you even solve this thing in terms of parameters? It's complicated. But what we can do is if we have some estimates of the parameters, we can say, well, okay, so maybe we can't give some sort of full parameter space description of what's going on. But we can ask ourselves something like, how does this set of equations depend on one parameter, like the carrying capacity? And that's what we're going to do here. So we're going to say for a fixed set of parameters, given at the end of question 1, before question 2, we want to think about what the effective varying K is. And so we'll go through, so this will work us, we'll find the null lines in this case, and we'll look at the behavior that happens when we vary K. And because what it turns out, and you'll start to see this and convince yourself of this, that when you really, really understand the behavior that you get, the changes in behavior you get when varying K, that you actually pretty much understand what can happen within the system. So we're going to go through and describe that pretty completely. And at the very end, I'm going to ask you to compute the stability type of one of the equilibria. So if you have questions, this can be a bit of a difficult computation. And if you want to do it by hand, I don't know. This is definitely the kind of computation where if you sit down and you just grind it out by hand, it'll probably just take you 10 minutes to compute the Jacobian. It's not that bad. It's just kind of a pain. But I want to invite you in to something here, which is using SymPy. So at least one of you has already started doing this. Well, one of you started doing this at the very first assignment in the class, so at least one of you is well aware of SymPy. But at this point, I trust that you guys can do brutal algebra. And so I'm definitely going to allow you from here on out to do your calculations using SymPy. So SymPy basically, it's the symbolic Python. And what it allows you to do, I'll show you a quick example here. So you can define symbols, and then you can define expressions in terms of symbols. It plays very nicely with Jupyter. So you'll notice that it's latexed this up, right? And it allows you to do all sorts of things, including differentiation, integration, solving differential equations symbolically, forming matrices. I think this will even diff. There we go. So it takes the derivative there plus x, sorry. Plus x times x, great. There we go. It does everything. It'll do things symbolically, and it plays nice with Jupyter's tech output. So if you want to make a matrix as an example, and take the derivative of everything in the matrix, as you may want to do when you're taking the Jacobian, this is a much simpler way to do it and allows you to keep track of everything nicely and symbolically. You don't have to do this. It might take you less time to just do it by hand than to learn SymPy. But I want to give this, I want to open this up as a tool that you can use, and basically give you my blessing to use it for the rest of the class. So for the rest of the class, as long as you show your calculations one way or another, you're more than free to use SymPy to do calculations. And I would encourage you to try it out. You know, there's a lot of power in there. So, all right. So I'm really sorry that I went 10 minutes over here. I'm cramming a lot of material, in. But thank you all for your patience. And if you have any questions, please ask. And I will see you next week, if not before.
Professor?
Yeah.
For the last example, you talk about the I, like in the notes, talk about the I, like the population goes to 0, and you graph the picture. Could you please explain that a little bit? Because I'm a little bit confused about that.
Yes. Okay. Right. So yeah. Thank you. So basically here, so you're asking about this, right?
Yes. No, not this one, but the one below this.
Oh, okay. Yeah. Right. So what happens here? So so I was thinking about what we're looking at is evaluating a certain strategy. So in this case, the strategy is culling or just removing some percentage of the population. So that is some percentage of the healthy population, some percentage of the unhealthy population. This would be something like setting traps or something that are just so practically what that does, right, is that shifts the mortality rate. Just by some constant, you know, okay, we're taking away 20% more per year, great, and the mortality rate is what it was before plus 20%. And so then we can ask, well, how does this affect our picture, right? So essentially what we're doing is we can see that the parameter effect is that throughout the system of equations, we're just increasing A. So looking at the trace, what this is doing is acting as a shift in A here. So we can say, so okay, we can try to work out analytically what effect it has, or we can kind of go back to this picture and say, well, how does this picture change as we increase A? Okay, and luckily, so here we've drawn everything on, right? We have our asymptotes and we have our null-clines and whatnot, and we can see that actually what happens is we increase A, then this asymptote, so the horizontal asymptote for the null line decreases. So as we increase A, it goes down, right? That's how A shows up here. And similarly, as we increase A, the vertical null line shifts. It shifts up in value. So we have this effect of increasing A shifts this equilibrium down and to the right. And that, in fact, 0 isn't a barrier for it. We can absolutely take this null line to 0 or below it. Doesn't change. There's all that we're doing in that case, right, is we're just saying, oh, when we take it to 0, then the birth rate is exactly the same as the death rate. If we take it below 0, then we're saying that the death rate is higher than the birth rate. So the death rate with culling is higher than the birth rate.
Thank you so much. But how can you see this from the diagram? Like you draw the picture in the lab, and you tried 0.2, and you said that is the point, like the value of the K, and that the population goes to 0. I'm sort of confusing that point.
Oh, yes. So actually, that's an analytic computation. So basically, yeah. So I kind of skipped over that. So we can ask, so when does the trace actually become less than 0, right? When do we flip from stability to instability? And so here, in this case, we actually, right, I actually have values for each of these things, right? So B minus A and alpha. So B is 0.3, A is 0.1. So here, B is 0.3, A is 0.1, alpha is just 3. And so in this computation, we have 0.3 times 0.3 minus 0.1 minus K, and then 0.3 minus 0.1 minus K minus 3. And so this is pleasantly less than 0 and stable, right? For basically, yeah, we actually put an equality in there. Okay, so this just is equal to what's 0.3 times 0.2 minus K, 0.2 minus, minus 2.8 minus K. So in this case, the denominator is actually not going to be affected, right? And this is going to be merely less than 0 until K is greater than 0.2. Right, so as soon as K is greater than 0.2, then the sign of the numerator flips. And I apologize because I think I said the sign of the denominator when I went through this. I think I was pounding on the denominator being the thing that changes sign. In this case, it will be the numerator that fixes that changes things.
Got it. Thank you.
Cool. Absolutely. Any other questions? All right, fabulous. Let me know if you have any other questions, whether it's about the lecture, the assignment, or the final project, and I'll revisit the final project dates a little bit and make sure that everything is where it needs to be. I would also say do feel free to contact me. I will probably reach out to you at some point and check where you're at, but it's I am more than happy to be in dialogue with you guys about the final projects in a fairly consistent way. I mean, certainly with in the machine learning class, the final projects are a bigger portion of the grade and a bit chunkier. You know, I will typically have weekly meetings with all of the students in all the student groups. So don't be shy about reaching out, and I will almost certainly reach out to you guys at some point next, just to ask you where you are and what you're thinking about. So take a look at those SIR models. I broke up basically what kind of thing the different models are. For those of you that are interested in taking probability 1 in the fall, which I'd highly recommend, Dr. King is looking at incorporating some of these Markov models and discrete models into his course. So that should be super interesting. And yeah, have yourselves a fabulous morning, afternoon, or evening, depending on where you are. And I'll see you next week, if not before. Absolutely.